In this chapter, we will discuss different acids and different bases and the reactions. We will also learn how to draw chemical reactions, find the direction of equilibrium, and the factors that affect acidity and basicity. So, to start with, the most common organic reaction is the reaction between a nucleophile and an electrophile. A nucleophile is a species that has electrons. So, normally the nucleophile is an electron source, and the electron source should have electrons in there. So, the reaction always starts from the nucleophile. And the way that it starts is you start with the lone pairs always. So you have to locate where your lone pairs are. And it's going to start from the lone pair. And you're going to show that these lone pairs are being shared in order to make a covalent bond with an electrophile. Electrophile is a species that lacks electrons. It needs electrons. And that species normally has either a solid positive charge or a partial positive charge. Normally, a partial positive charge is formed whenever you have an electronegative element in there next to a hydrogen, for example. So here you are forming a direction of polarization because the chlorine is more electronegative. So the chlorine is going to pull electrons away from the hydrogen. So think about it like this: chlorine pulling electrons away from the hydrogen and making the hydrogen partial positive. So this hydrogen over here is going to be lacking electrons because of the chlorine. So this is why if you have an electron source like a nucleophile, then you're going to have an immediate reaction where the nucleophile is going to share its electrons to make a covalent bond with the hydrogen. So nucleophiles are source of electrons, and the nucleophiles can either have a lone pair or they can be in a form of a double bond and a triple bond. Remember that a double bond is an overlap of two p orbitals. And we know that in each p orbital, there is an electron in there. So when the electrons overlap, they make a pi bond. So if this pi bond is broken, I can make use of these two electrons, and I will have a source of electron in there to make a covalent bond with the electrophile. Same thing as the triple bond. Triple bond is also considered to be a source of electron, and a triple bond again is made up of um, these two p orbitals in there, each one of them, the py's, they overlap to make a pi bond. And they are also made up of the pz that can overlap to make another pi bond. So to make another pi bond in there. So I can break one of these pi bonds and I can make use of the two electrons in order to share those electrons with the electrophile. So the common reaction is the general reaction is the nucleophile reacting with the electrophile. Always start your arrow from the source of electron. So you have to locate your source of electron towards the electron deficient species, towards the electrophile in there. And what I'm doing over here is I'm creating a covalent bond because I am sharing those electrons with the electrophile. So you're going to end up getting your product. The types of acids and bases are Bronsted and Lowrey acid base and Lewis acid Lewis base. Let's start with the first one, the Bronsted and Lowrey acid. By definition, Bronsted and Lowrey acids, they should have a hydrogen because they donate their hydrogen. They give their hydrogen away to the base. So this is why we call them hydrogen donors. And the Bronsted and Lowrey base should have a lone pair or any source of electron, like a double bond or a triple bond. So by definition, a base is a source of electron. So that base here needs to be a source of electron. Whether the source of electron is in a form of a lone pair, whether it's a double bond, whether it's a triple bond, it needs to be a source of electron so that the reaction can start with. So that the reaction can start with the electron, and then it's going to share its electrons with the acid, meaning that the base always takes the acidic hydrogen. Base takes the hydrogen of the acid always. There are different bases ranging from negative charge small bases, neutral bases, and bulky bases. By definition, a negative charge base is a strong base. And there's a big difference between a strong base and a weak base. A strong base reacts immediately. A weak base takes time to react. So strong bases, we know them by the negative charge. So the moment we see a base having a negative charge in there, then immediately that is going to be a strong base. How can we locate the negative charge? Normally bases have negative charge if they are ionic. So you need to start with a metal like a group 1 or a group 2 metal in there, like sodium, potassium, calcium. Normally the most common metals that we use are sodium and potassium. So whenever you see those, then this means that you are talking about an ionic bond. So definitely the polyatom that comes and bonds with the metal, this needs to be an ionic bond in there. This is called sodium hydroxide. You are responsible to know the names of these bases. This is sodium hydroxide. This is sodium amide. Whenever you name the base, you name the metal part first, which is the positive part, and then you name the polyatom. This is sodium methoxide. Meth is whenever you're working with one carbon. F is whenever you are working with two carbons. And the oxide means that the F is connected to the oxygen, and here the meth is connected to the oxygen as well. Notice that the oxygens in there, the nitrogen, the oxygen, all of those, I am putting their formal charges. They have to be negative. Oxygen here is doing one bond with the hydrogen, 3 lone pairs, so it is a negative charge. Nitrogen here is doing 2 bonds with the hydrogen, then it needs to have 2 lone pairs. So here I'm missing a lone pair. Let me go ahead and add that. So nitrogen should have 2 lone pairs, negative charge and 2 bonds. Oxygen is a negative charge here, and the hydrogen is a negative charge. All of those, since they are negative charges, we are going to classify them as small bases, and they are strong bases as well because they are negative charges. Now, with respect to the neutral bases. Neutral bases, they have no charge. But notice here that, again, bases, they are source of electrons. So the bases should have lone pairs. So this is the basic part of the water. So you look at the element that has the lone pair, and this is the basic part. So this is the basic part. So this is where the reaction where it starts. This is the part where it starts donating its electrons to take the hydrogen of the acid. All of those, they are zero formal charge. So these are considered to be bases because they have lone pairs and they are neutral. Neutral bases are classified to be weak bases. So if I am to compare between strong bases and weak bases, strong bases, they have negative charges. Weak bases, they are neutral, they have zero formal charge. Now you can see the difference between those bases in there, which is kind of like small bases, compared to the bulky bases that you have over here. This is called potassium tertiary butoxide. We're going to use this base a lot. I've written it in its condensed form here. This carbon is connected to 3CH3s, and this is how you write it in its skeletal form. You have a carbon connected to 3CH3s and oxygen in there and K plus. It's either potassium or sodium. This is called a bulky base. Bulky because the R group, which is connected to it, the R means carbons. So you have the carbons that are connected to it. These are branched carbons. So this is why we call this a bulky. But since it is a negative charge, it is considered to be a very strong base. Nitrogen, the same thing over here. It has two lone pairs and it has this bulky group over here. This is an isopropyl group. We will work with namings as we proceed. And iso is this form. You have a CH connected to two CH3s. This is called an iso. So whenever you have a CH connected to two CH3s, this is called an iso group. And the propyl is three carbons. So count here, it's 1, 2, 3 carbons. So this is why it's called an isopropyl. It's an amide because there is a nitrogen. It's 2 isopropyl. So this is why we use the prefix di. This is abbreviated as LDA, and this base, we're going to use it a lot in organic. These two are the only bulky bases that we will be using in organic. Okay, so these are the examples of bases in there. Now for the Bronsted and Lowrey acids. So Bronsted and Lowrey acids, they should have an acidic hydrogen. They should have an acidic hydrogen. So hydrogen is a must. And as you can see, these are the examples of Bronsted and Lowrey acids. They start with a hydrogen. So any of the halides, hydrogen halides, the sulfuric acid, water, hydronium ion, all of those are considered to be Bronsted and Lowrey acids because they start with a hydrogen. They have to have an acidic hydrogen. Now, what is an acidic hydrogen? An acidic hydrogen normally is a hydrogen that is connected to an electronegative element. Whether this electronegative element is a halogen, we represent the halogen by X, fluorine, chlorine, bromine, or iodine. Whether it is an oxygen, whether it is a nitrogen in there, all of those are considered to be an electronegative element. But the idea is that the more electronegative the element is, the more acidic is the hydrogen. Why is that? Let's compare hydrogen connected to a chlorine versus hydrogen connected to an oxygen in there, okay? Versus a hydrogen that is connected to a nitrogen. I'm just checking the bond in there and checking the acidity of this hydrogen. When you have a question on acidity, if you have compounds in there and I ask you which one is more acidic, well, you have to look and locate the acidic hydrogen and compare the partial positive charge of this acidic hydrogen. So this is why I highlighted the hydrogen in there that is connected to the electronegative element. The rule says that the more partial positive the hydrogen is, the more acidic is the hydrogen. So how can I determine this? First of all, you need to figure out the direction of polarization based on the electronegativity, meaning the flow of electrons. I know that chlorine is very electronegative, right? Because electronegativity increases from left to right in a period and from bottom to top in a group. So chlorine is more electronegative than oxygen, than nitrogen. So chlorine is going to pull electrons more from the hydrogen and make it more partial positive. So that hydrogen is going to be more partial positive than the oxygen, or then the hydrogen connected to the oxygen, then the hydrogen connected to the nitrogen. All of those are polar covalent bonds. Okay, but the pull of electrons from the electronegative element in there is more. So from this chlorine is more. So it's going to make this hydrogen in a desperate need of electrons. So it will be more electrophilic. So if I am comparing now this hydrogen that you see here, it's going to be more electrophilic. So if it is more electrophilic, this means that it is more acidic. So the idea is the more partial positive the hydrogen is, the more acidic is the hydrogen. There is a difference between hydrogen that is connected to elements that belong to the same period In this case, you need to look at the electronegativity and the pull of electrons to determine how partial positive this hydrogen is. And of course, the more partial positive the hydrogen, the more acidic it is. And hydrogens that belong to, or they are connected to elements that belong to the same group. Like, for example, chlorine, bromine, iodine, and fluorine. If you look at the periodic table, this is elements belonging to the same group versus elements belonging to the same period. Same period, you look at the electronegativity, but same group, you have to look at the size of the ion. Why I am saying ion? I'm saying ion because you have to change each one of those acids into their conjugate bases. So if I am comparing hydrogen that is connected to iodine versus hydrogen that is connected to a bromine versus a hydrogen connected to chlorine versus a hydrogen that is connected to the fluorine, you would need to change each one of those acids into their conjugate bases by simply removing a hydrogen. So Hi will be I minus, this is the conjugate base. The conjugate base of HBr will be Br minus, this one will be a Cl minus, and this one is going to be an F minus in there. Now, because I am dealing with the ion, and there are different sizes for these ions because we know that the atomic size increases as you go down the group. So I am expecting that I minus is a bigger ion than F minus in there. So if I want to represent the size of the ion, let's go ahead and represent it by a small ball. Okay, so I minus here is going to be a larger circle with a negative charge compared to the Br minus, which is going to be a little bit smaller, compared to the Cl minus, which is going to be even smaller, and compared to the F minus, which is going to be smaller. So just to check with me over here the distribution of this negative charge across the surface area. You can easily see that the negative charge here is more distributed over a larger surface area. This is going to stabilize the ion. So this is why I minus here is stable, because the charge is distributed over a larger surface area. And the more stable the conjugate base, the more acidic is the acid. So this is why Hi is the strongest acid among all of these acids. Acid-base reactions are very important in organic. So in these types of reactions, an acid reacts with a base. We cannot have a reaction between two acids. We cannot have a reaction between two bases. But we can have a reaction between a base and the acid. Whether the base is a neutral base, which is a weak base, or the base is a strong base, which is a negative charge base, small or bulky, the reaction can easily happen. And the reaction happens as such. This is the general form of the reaction. Acids are represented by an HA. Bases are represented by lone pairs. So your arrow always starts from the base. So you have to locate always your base in there. This is the Bronsted and Lowrey base. By definition, these bases, they take the acidic hydrogen. So you have to locate your acidic hydrogen that is connected to the electronegative element. This is the electrophile. The base is the nucleophile. So your arrow is going to go from the nucleophile towards the electrophile. Now, whenever we're working with these reactions, every time you make a bond, because here you're making a bond between the base and the hydrogen. So see, you're making a covalent bond, you're sharing the electrons between the base and the hydrogen. So every time you make a bond, you have to break a bond. This is the rule for reactions. So when you break the bond, we know that the bond is made up of two electrons, right? So this bond is two electrons. So these two electrons will be added to the A, as you can see. So the two electrons here will be added to the A. Always the acid will turn to be a conjugate base, and the base will turn to be a conjugate acid. So this is the general reaction. Let's go ahead and have some examples in there. We have HBr. So let's start with HBr. And we are reacting this with sodium methoxide. Now, normally in organic, we drop the positive part. So it's not necessary that I show you the sodium. I would show you the OCH3, and you should know that the oxygen, because it is making one bond with the carbon, then it needs to have a negative charge in there. The type of bond between the sodium and the oxygen is an ionic bond. Okay, so let's go ahead and look at this reaction in there, and let's write the product of the reaction. The first thing here is to draw the lone pairs. This is the first thing. The second is to locate your base. Now, bases, they are neutral or they have a negative charge. But the moment you see a negative charge in there, then this is going to be your base. So you locate the negative charge. Where is the negative charge on which atom? And this is the basic part of the molecule. I didn't choose the bromine because the bromine is connected to the hydrogen, and the hydrogen here is the acidic part. So this is going to be my acid, so definitely this is going to be my base. This is the source of the base, so the electrons are going to start from the oxygen in there. So I'm having here my acid, so this is going to be my acid, this is going to be my base in there. And the reaction starts from the lone pairs of the base towards the hydrogen of the acid. This hydrogen, as we said, is partial positive. It is an electrophile in there. Okay, so this is why here I'm having a reaction between the electrophile and the nucleophile. The nucleophile is the oxygen of the base. So the arrow starts from the lone pairs, not from the oxygen, not from the negative charge. It starts from the lone pairs towards the hydrogen. I am sharing two electrons, so this is why I'm using a double head arrow and a full head arrow actually. In this case, every time you make a bond, so I'm making a bond between the oxygen and the hydrogen, you have to break the bond. So I'm going to break the bond between the bromine and the hydrogen, and I'm going to add the electrons to the bromine in this case. So my product here, I made a bond between the hydrogen and the oxygen next to the CH3. So this is the new bond that I made. This is the bond that I made over here. So go ahead and write it down, plus whatever is left. So bromine here is left. Bromine already has 3 lone pairs, and I added 2 more. So you're going to end up having your bromine with the 3 lone pairs, and I added 2 more. So these are the 2 that I added in there. Bromine now is fully charged, so this is why the Br is a formal negative charge. As we said, that the acid always changes into a conjugate base. Guys, remember that negative charges is a sign of basicity. So Br, because it's negative, it has to be a base. It has to be a conjugate base. Bases always change into conjugate acids in there, into a conjugate acid. Okay? Now, if I am looking at this reaction in there, I want to determine the equilibrium of the reaction, because we know that the direction of equilibrium can go either to the right or to the left. Now, if the direction of equilibrium goes to the right, the reaction is going to happen. But if the direction of equilibrium goes to the left, then in this case, the reaction will not happen. So this is why I want to know if the reaction happens or not. To do this, you have to compare the acids, which is way easier than comparing the bases. So always look at the conjugate acid and the acid. There is a pKa table that I posted on eCampus, and this is the pKa table in there. The rule says that as the pKa increases, as the acidity decreases. So as the value of the pKa becomes larger, as the acidity is going to decrease. In this table, the strongest acid is the HI, and the weakest acid is simply the alkane because it has a very large pKa. So this is where you are going to find your pKa values, and this pKa table, you can have it in the exam as is. Okay, so by looking at the HBr, you look at the acid and the conjugate acid, and then you look at the pKa table in there. So we know that HBr, it has a pKa of -6. So you write down the pKa of HBr. So this is pKa of -6. And then the alcohol has a pKa of 15.2 from the table. All of these values, I'm getting them from the table in there. And if you take a look at the alcohol, this is the CH3OH. This is it, and this is from where I got the value in there. And as I said, as the pKa increases, as the acidity is going to decrease. So in this case, if I am comparing between the two pKa's, this is a smaller pKa. So it's going to make the HBr to be more acidic. So as the pKa increase, as the acidity decrease. So I am expecting that HBr to be more acidic than the methanol in this case. So the direction of equilibrium always lies away from the most acidic or from the smaller pKa. Okay, so the direction of equilibrium in this case, since HBr is in the reactants, then the direction of equilibrium is going to lie away from the acid, the most acid. So the direction of equilibrium here is going to be to the right. This means that the reaction is going to happen. Okay, let's have another example. Another example here is sulfuric acid. So always with these types of reactions, please write the Lewis structure. This is why we studied the Lewis structure, to write the Lewis structure in there. So if we have sulfuric acid, again, the moment you see an acid, this is definitely going to be your acid in there. And either one of these hydrogens are going to be taken by the base. So you're going to react this with, let's say, water. Whenever you dissolve acids and water, it doesn't matter what type of acid that is, acid and water is going to give you a hydronium ion. So here I have my sulfuric acid. This is going to be my acid in there, okay? And water is going to definitely be my base from the oxygen. Now notice here, I didn't use these oxygens to be a basic source, because this is an acid. So if it is an acid, I have to use the hydrogens of one of these hydrogens in there to be my acidic hydrogen, because this hydrogen here is more acidic than the hydrogen that is connected to the oxygen in the water. So this is going to be my acid, and that is going to be my base. Okay, so as I said, arrow is always going to start from the base towards the acidic hydrogen in there. Every time you make a bond, you break a bond, and the electrons are going to be added to the oxygen. So your product in this case is going to be sulfur double bond O, double bond O. You broke the bond between the oxygen and the hydrogen. You added the lone pairs, so you added these lone pairs in there. So now your oxygen, based on the formal charge, your oxygen is going to be a negative charge in there. Plus, you made your hydronium ion. Every time you dissolve any acid in water, you are making your hydronium ion. Okay, this is going to be your hydronium ion in there. So when we said that acids always turn into conjugate bases, and bases always turn into conjugate acids in there. After all, the negative sign is a sign of basicity. Whenever you have oxygen with a positive sign, this is a sign of acidity. So one of these or all of these hydrogens, they are considered to be acidic hydrogens because they are next to an oxygen with a positive charge. After all, oxygen also is an electronegative element in there. Let's go ahead and determine the direction of equilibrium. To determine the direction of equilibrium, again, we're going to go ahead and look at the acid and the conjugate acid. Okay, so look at both from the pKa table that I just showed you. So get the values. The pKa of the sulfuric acid is around 5, okay, and the pKa of the hydronium ion is around -2. Okay, I'm sorry, this is around -5. It's not 5, it's -5 in there. This is going to be a lower number. So this is going to be a stronger acid. So the direction of equilibrium always lies away from the stronger acid. So this is why it's going to lie to the right in there. So the reaction is going to happen. Now, the way to represent it with an equilibrium arrow, you simply represent it as the direction of equilibrium lying to the right, and a small portion of the arrow is lying to the left. So this is how you represent it in there to show that your reaction proceeds to the right. Another example is, let's go ahead and dissolve. Again, as I said, any acid, when we dissolve it in water, we're going to go ahead and form a hydronium ion. So this is the acid in there. And notice that I always, whenever I write a chemical reaction, I always show the lone pairs. This is a must in there. Now, both have hydrogens, but I know that chlorine is way more electronegative than the oxygen. So this is going to make my acid in this case. So this hydrogen here is going to be my acidic hydrogen. So this is going to be my acid. Then definitely this is going to be the base. If it is the base, then I'm going to choose my basic site, which is the lone pair. And I'm going to start my reaction with the lone pair. So the lone pair here are going to come and take the acidic hydrogen and add the electrons to the chlorine. Every time I make a bond, I'm making a bond between the oxygen and the hydrogen. You have to break the bond and add the lone pairs to the chlorine. So again, I am forming my hydronium ion. I'm doing these examples just to show you that any acid, whenever it's dissolved in water, you're going to get your hydronium ion. And as I said, that the positive charge is a sign of acidity, then this is going to be my conjugate acid. Plus, of course, whatever is left from the acid, it's the Cl minus in there. I added an extra lone pair on the chlorine, so it's fully charged now, and that is a negative sign. So definitely it's going to be my conjugate base in this case. Let's again check the direction of equilibrium of this reaction by simply locating the acid and the conjugate acid. So you look at the acid, you look at the conjugate acid, and from the pKa table, guys, determine the pKa. So the pKa of HCl is around -4. The pKa of the hydronium ion is around -2. Of course, -4 is going to be smaller, so it's going to be more acidic. So again, the smaller the pKa, the more acidic is the acid. So -4 here is going to be smaller than -2. So in this case, it's going to be more acidic. So this is why the direction of equilibrium is going to lie always away from the more acid or the more acidic acid. So the direction of equilibrium is going to be again to the right. And you represent it by an arrow going all the way to the right and then a small arrow going to the left, like that. Additional examples in there. Let's see if we have methanol or ethanol. Let's do ethanol in there. So a CH2OH. And I am reacting this with a base. Now, just a second in there. What I'm going to do in the exam, I'm just going to show, whenever I show the base, I'm not going to show any lone pairs or anything like this. I'm just going to show it like that. So this is sodium amide. You need to know that the sodium is group number 1, so it needs to be positive charge because it makes an ionic bond. Then definitely the nitrogen needs to balance that positive charge, and it needs to be a negative charge in there. Nitrogen is negative when it has two lone pairs and two bonds. So you would need to be able to fill all the lone pairs and everything around that. Now, since the nitrogen is a negative charge, this is going to be a strong base. So that is going to be my base from the nitrogen. So this is going to be my basic site in there. Then definitely this hydrogen over here is going to be the acidic hydrogen. Now, why did I choose this hydrogen and not the hydrogen connected to the carbon? Well, oxygen is more electronegative than carbon. So this is why this hydrogen is more partial positive than this hydrogen over here. So this is why it's more acidic. Okay, this is why I'm choosing this hydrogen. After all, the base is going to choose the most acidic hydrogen and grab it. So the arrow is going to start from the nitrogen. So it's going to start from the nitrogen towards the acidic hydrogen in there. And every time I make a bond, I break a bond. So the bond between the oxygen and the hydrogen is going to be broken, and the electrons will be added to the oxygen. Let's go ahead and write it in a better way, just to represent this bond in there. So this is going to be my acidic hydrogen, so that you would see that the bond's going to be broken and the electrons will be added to the oxygen. So now I'm going to end up having my oxygen over here with a negative charge, plus, of course, the NH3 that took a, or NH2 that took a hydrogen and becomes an NH3. So you can simply write it like this, or you can write it as an NH3. It really doesn't matter. Okay, here you go. I used one lone pair, so I still have another. There is no charge on the nitrogen. So here you go, and this is going to be your ammonia. In this case, that is going to be formed plus. Okay, now let me note something, that always the charge of the reactants needs to be exactly the same as the charge of the product. Meaning that if you start with a zero charge reactants, then your products have to be a zero charge. This means that, see that oxygen with the negative charge, it will definitely be balanced by the sodium in there. Even though if we don't write, normally we don't write the cation, the metal, the sodium or potassium, we don't write it, but it is there. Okay, so that O negative normally is balanced by the Na plus. Let's go ahead and write it down. Every negative charge should have a positive charge that balance that. So this is going to be my acid. You have the base. This is going to be the conjugate base now, and this is going to be the conjugate acid. Again, conjugate bases, they have normally negative. Whenever you see a negative charge, this is immediately going to be a base, and definitely it's going to be the acid. To determine the direction of equilibrium, as we did before, go ahead and locate the acid and the conjugate acid, and go ahead and check the pKa's of those from the pKa table that we have. So the pKa over here is 16 versus the pKa of ammonia is 36. Of course, this is going to be a lower pKa, so it's going to be a stronger acid. So the direction of equilibrium always lies away from the stronger acid. So when I express the direction of equilibrium, it's going to be like that. Way more towards the reactants, or I'm sorry, towards the products, and a little bit towards the reactants. Another example is, here you go. So if I have something like this, plus Na. Of course, there are more examples in the notes. Please make sure to go over those. Here you go. Okay, so if I have something like that plus the sodium, okay, I know that this is going to be my base because it is a negative charge. Now for the acid. So what do I have here for the acid? Take a look at this carbon. This is a CH3. So I have a hydrogen here, and a hydrogen here. This is symmetrical because this CH3 is similar to the CH3 over there. So just pick a hydrogen on the CH3. This is called an alpha carbon. An alpha carbon is a carbon that is directly connected to a carbonyl. And this alpha carbon is an sp3. I know that it's an sp3 hybridized carbon. This is an sp3 hybridized carbon. However, This sp3 hybridized carbon is connected to an sp2 hybridized carbon. By definition, an sp2 hybrid carbon is more electronegative. So if I want to draw the pull of electrons or the direction of polarization, it's going to be from the sp3 to the sp2. This is how the pull of electrons is happening in there. And of course, the oxygen is the most electronegative, so the oxygen is pulling electrons in there. So the flow of electron is going from the carbon to the sp2 carbon to the oxygen, leaving these hydrogens in there to be partial positive. So I located my acidic hydrogen in there. So all of those are partial positive. Now, how acidic they are slightly acidic. They are not very acidic because they are connected to an sp3 hybrid carbon. But they are acidic enough for this strong base to come and take one of these hydrogens in there. So I'm just going to go ahead and highlight one of those hydrogens. They are all the same. Just one of them to be my acidic hydrogen. So to draw the flow of electron, it's going to be from the base towards the acidic hydrogen. And I'm going to break the sigma bond and add the electrons to the sp3 hybrid carbon. So my product in this case is going to be, this is an O, okay. You're going to have a hydrogen here, a hydrogen there. You added the electrons, then definitely this is going to be a negative charge because a carbon with the 3 bonds and a lone pair is a negative charge. You can either express it like this, or you can simply draw it in its skeletal form. Please get used to that. Okay, get used to the skeletal form, not showing the hydrogens. So these two are the same. Plus, of course, I did make a bond between the oxygen and the hydrogen. Okay, so this is going to be my new bond that I made, the covalent bond between the oxygen and the hydrogen. Because this guy is a negative charge, then this is going to be my conjugate base. Then definitely this is going to be my conjugate acid. This is going to be my base, and that is going to be my acid. This is the acidic hydrogen in there. Direction of equilibrium, all what you need to do is just go ahead and read the pKa from the table in there. From the pKa table, this is listed as, let's go ahead and see. This is listed as a CH3. Okay, here you go. So a CH3CO, CH3, this is it. So it's a pKa of 19. So this is a CH3. This is the condensed form, CO and the CH3. The CO is a carbonyl. So the CO is basically the CO over here. So the pKa for this one is equal to 19. And the pKa of the conjugate acid, again, look always at the acids in there. This is 17. So I know here, this is my first example. This is the first example of direction of equilibrium going towards the left. So going towards the left, this means that the reaction will not happen. This pKa is smaller, so this is going to be a stronger acid. It's going to be a stronger acid. So if it is a stronger acid, then the direction of equilibrium is going to lie away from the stronger acid in there. So when I am drawing the direction of equilibrium in this case, the direction of equilibrium is going to be towards the reactants and a little bit towards the products in there. So this means that the reaction lies to the left. And if the reaction lies to the left, this means that the reaction does not happen as written. So it does not happen as written. Okay. Another example is if I have a triple bond. Or one more thing, if the reaction doesn't happen as written, this means that you need to reverse the reaction. This means that the products need to be reactants and reactants need to be products for this reaction to happen. But all what you need to state is that the reaction does not happen as written because the direction of equilibrium goes to the left. Another example is if I have an HC triple bond, CH. This is now a triple bond, and I am reacting this with sodium hydride. Okay, again, the moment I see sodium, I know that sodium is plus a charge, then definitely the hydrogen needs to balance that. Then definitely I have an ionic bond. H minus, this is going to be my base. So that is going to be my basic part in there. Then definitely the hydrogen here is going to be my acid. Okay, so I have my acid, I located my acid, I located my base. Let's start the reaction from the base towards the acidic hydrogen. Every time I make a bond, I break the bond, and you're going to end up having the triple bond. This is a C. I added the lone pairs with a negative charge, and there, plus, of course, I formed hydrogen gas. I formed H2 because I made a bond between this hydrogen and this hydrogen over there. As I said, every time you have a negative charge, you should have a positive ion to balance it. But it's not necessary that we show it in the organic reactions. Normally, we don't show it. But even if we don't show it, this doesn't mean that it is not there. By the way, this ion is called an acetylide ion. And this ion, normally we represent it by its skeletal form like that. Okay, so these two are the same. You don't show the carbons. So you have a carbon here, you have a carbon there, and you don't show the hydrogens as well. To determine the acidity, we need to look at the acid and add the conjugate acid. So you have your acid here. This is the base. This is the conjugate base, and this is the conjugate acid. Again, this is the conjugate acid. Again, bases, they have negative charges. So this is why this is considered to be a conjugate base in there. Acids change into conjugate bases. Bases change into conjugate acids. Determine the pKa's. So here I have the pKa. This is a triple bond. If you look at the pKa table of the triple bond in there. So this is going to be my triple bond. Now, normally you won't find the exact, if you don't find the exact structure, just go ahead and estimate. This has a triple bond. Now, this is the exact structure of this one. But let's say, for example, if I have a carbon next to that triple bond, just go ahead and estimate. So you would say that the pKa is approximately 26. And there. So the pKa here is 26 versus the pKa of the hydrogen, which is equal to 35. So definitely this one is going to be a stronger acid. And if it is a stronger acid, then the direction of equilibrium is going to lie away from the stronger acid. There are multiple examples in the class notes in there. So please go over these examples as well. To change bases to conjugate acids, we normally add hydrogens. So conjugate bases in there, just add the hydrogen and become a conjugate acid. If water is an example of a base and an acid at the same time. So if water behaves as a base, then you have to consider the lone pairs of the water. But if water behaves as an acid, you have to consider the hydrogens in there. Okay, so we've considered before water behaving as a base. Let's have an example of water behaving as an acid. So if I have, like, for example, this reaction in there, and I am reacting this with the following. So I have a CH3 with a negative charge. Of course, there is sodium in there to balance that base. Okay, so in this case, this is going to be my base, right? So if I have the nitrogen to be my basic source, then definitely now water is going to act as an acid from the hydrogen. So this is going to be my acid, and the arrow is going to start from the base. It's going to take the acidic hydrogen and add electrons to the oxygen. So you're going to end up getting your conjugate acid in this case. So this is going to be my CH3. This is going to be my hydrogen in there. And this is going to be my conjugate acid. Plus, the OH minus is going to leave. And that is going to be a negative charge. Then this is going to be my conjugate base. To determine the direction of equilibrium, as always we do, you locate your acid. So this is going to be your acid and your conjugate acid. And determine the pKa of the acid and the conjugate acid. So the pKa for water is around like 15 or 15.7, and the pKa of the conjugate acid is around 36 in this case. So we know that the direction of equilibrium lies away from the stronger acid. So the direction of equilibrium lies to the right. This reaction happens. So when we express the direction of equilibrium, we express it as to the right and then a little bit to the left. To change acids to conjugate bases, just remove a hydrogen and you're going to end up getting your conjugate base.